So, students, from the last class I have told you about some basic properties of cathode rays. Basically there are, I have taught you three basic properties. First one is the cathode rays travels in straight line paths. Okay. Then the second one was cathode rays possess momentum. Okay. So, the particle nature was proved, investigated by the Thomson's experiment of that light paddle wheel case. Okay. So, as the light paddle wheel rotates, it confirms that the cathode ray has a particle nature or a momentum. So, after that we can call them as cathode ray particles, because there is a particle nature there. Okay. Cathode ray particles. Then after that I have told you the electrical properties. So, the next one was the cathode ray particles are electrically charged. There is an electric charge. Okay. So, they possess an electric charge. So, when cathode ray particles travels perpendicular to a magnetic field, it shows a deflection in a perpendicular direction to the direction of the magnetic field. So, it confirms there is a charge. Then as I told last time, so the Thomson's mind, in Thomson's mind it comes after that, because there are only two type of charges in the world, either positive or negative. Then he planned his experiment, another experiment, to find whether cathode ray particles are negatively charged or positively charged. This is very simple physics experiments. So, we can just use electric plates, positive plate and a negative plate. Okay. It is very simple. We can use two plates instead of the magnetic field. Now, we use electric field. Okay. For that, we take the same setup, cathode ray tube as earlier. So, all the other setups are, all the other things are there. Okay. Vacuum pump, high voltage supply, they all are there, but I am not going to mark them. So, here have the cathode, negative terminal, and then the positive electrode, anode. So, we can mark this is the cathode, this is the cathode, and this is the anode. Okay. What he did was, okay, he placed two electric plates in the two sides of the cathode ray tube, like this way. Okay. Then he connected this one to external supply. Let us see, like this, electric supply, and there is a battery or electric supply is there. So, the positive terminal is this, negative. Then as this plate is connected to, this is an metallic plate connected to positive charge, this get a plus charge and this get a minus charge. So, he places a positive plate, and this is a negative plate. So, with these electric plates, positive and negative plates, he created an electric field in between plus and minus two plates. Okay. So, the thing is, as we know, opposite charges attract towards each other. Thomson observed that when he created an electric field using two plus and two metallic poles, like plates, like this way, the cathode ray particles, they are attracted. So, they are attracted towards the positive plate. So, this is the pathway. This is in dotted lines. I did noted that the pathway before placing two plates, and after that the plate, after placing the two plates, cathode rays are deflected towards the positive terminal, the positive pole plate of the electric field. Okay. So, this we can see that cathode rays are attracted to positive plate. This is very important. Cathode rays are attracted to positive plate. As the cathode rays are attracted to the positive plate, Thomson conclude that this cathode ray particle should be negatively charged. As we all know, opposite charges attracts. Therefore, in order for cathode ray particles to attract towards the positive plate, these cathode ray particles should be negatively charged. As they are negative, they attract towards the positively charged plate. Okay, this is very easy. So, after finding that there is an electrical charge in cathode ray particles, after that Thomson did this experiment to find whether the charge is plus or minus. Then he concluded that using this observation, cathode ray particles are negatively charged. Okay, write down number 4, fourth property. Number 4. Cathode rays are negatively charged. Number 4, cathode rays are negatively charged. Very important. Cathode rays are negatively charged. Negatively charged. Under that, write down the note. When two oppositely charged electric plates, are placed on either sides of the path of cathode rays, either sides of the path of cathode rays, either side of paths of cathode ray of the path of cathode rays, comma, the cathode rays are attracted towards, the cathode rays are attracted towards the positively charged plate, attracted towards the positively charged plate, positively charged plate. Therefore, cathode ray particle should be negatively charged. Cathode ray particle should be negatively charged. Highlight that word, cathode ray particles are negatively charged. That is very important. Okay. Now, right, now draw this setup. Okay, draw this. So, this was the fourth experiment done by the Thomson to investigate the charge of cathode ray particles. First one, investigate the property of the property of the cathode rays, that they travels in straight line. Number 2, they possesses a momentum over particle nature. Number 3, they possesses electrical charge. Then find in the fourth experiment, these cathode ray particles are negatively charged. That's important. Negatively charged. Draw it very neatly. Okay. Okay. Now let's see the next one. Let's see the next property, number 5. First of all, write down the property number 5. Then I will explain. Write down number 5. Cathode rays are originated perpendicular to the cathode surface. Now let's see what is that. So in all the 4 experiment, as you can see, in all the setups, you see a cathode in this shape, like this way. So it's like a flat one, no, flat cathode. Don't mark it like that. It's a flat one. The shape of the cathode is a flat. It's not like this flat, okay, flat one, okay, it's flat cathode. So in physics, okay, if we use the surface where the radiations originated, okay, so that's a place where the cathode rays originated, from the surface of the cathode. So if the surface is a flat one, okay, if the surface is a flat one, like this flat one, the radiations are originated perpendicular to the surface. This is due to the flat nature of the cathode. So it is due to the property of the cathode, okay, from any flat cathode, cathode rays are originated perpendicular to the surface. This origination of these rays perpendicular nature, is due to the shape of the cathode, because it is flat. So the reason is, as the cathode is flat, the rays are originated perpendicular. So the origination of the perpendicular nature of the cathode, so this is shown by the property of a cathode, okay, it's a flat cathode. So by using a flat cathode, we cannot investigate whether the cathode rays are originated perpendicular to the surface or not. So for that, what Thomson did was, so he changed the shape of the cathode. What he used was, he used a concave shape cathode instead of a flat cathode. So from a flat cathode, exactly the radiations are always originated perpendicular due to the flat nature. So in order to investigate the property of the radiation or the property of the cathode rays, okay, to investigate this property of the cathode rays, we need to use a concave shape cathode. Okay, concave shape cathode instead of flat cathode. Instead of flat cathode, we have to use, all the other setup is same. This is the cathode ray tube, that's okay. Cathode ray tube. Then we have the anode. So this is the concave shaped cathode. Concave cathode. So if I explain this in Sinhala, okay, මේ flat cathode එකක් use කරොත් ඒ cathode එක flat නිසා අනිවාර්යෙන් flat surface එකකින් perpendicular තමයි radiation එකක් යන්නේ අනිවාර්යෙන්. එතකොට radiation එකේ property එක surface එකෙන් perpendicular යනවා කියන එක අපිට හොයන්න බෑ flat cathode එකක් use කරලා. Therefore Thomson used a concavely shaped cathode for that. Concavely shaped cathode. Okay. So from concave shaped cathode, as you studied physics part in the O-level science, you know concave mirrors. There are mirrors called concave mirrors. So the concave mirrors are like circular. Actually, they are circular, no mirrors, but we use just only a part of it, like this. So we used a part of that. Okay, it's like a concave mirror. So for in a mirror, there's a center. It's like a circle. No? This center in a mirror is known as center of curvature. Center of curvature. Center of curvature. So the center of a mirror, concave mirror, is known as a center of curvature. Okay. So in a concave mirror, the radiations originated from the surface of the mirror passes through this center of curvature. So it's like they converge at one place, that is the center of curvature. So they converge, all the radiations converge at the same place, point. This point is known as the center of curvature. So if this happens, okay, so the radiations are converge into the center of curvature only if they are originated perpendicular to the surface of the cathode. Only if they are originated perpendicular to the surface of the cathode, they get converged into a one point, that is the center of curvature. So Thomson did the same thing, and he observed that the radiations cathode rays originated from the cathode surface, they are converged at the center of curvature. So in order for this to occur, the ray should be originated perpendicular. That's why they are converge at center of curvature. Okay. So after Thomson observed this observation, he concluded that in order for the cathode rays to get converged at the center of curvature, they should be originated perpendicular to the surface of the cathode. Okay, write down. When a concave shaped cathode is used, the cathode rays are converged to the center of curvature. Therefore, it confirms that cathode rays are originated perpendicular to the cathode surface. Perpendicular to the cathode surface. Okay, draw this. You can draw the concave cathode, then the center of curvature and the anode. So, this was the last experiment to investigate the properties of cathode rays. So, there are 5 experiments done by Thomson to investigate this. Number 1 is the cathode rays, the press properties cathode rays travels in straight line path. So, this was confirmed by using a metal cross on the path of the cathode rays, and it shows a image with a sharp edges. That is the first one. Second property is the cathode rays possess a momentum of the particle nature, that is confirmed by the rotation of the paddle wheel, okay, or the movement of the paddle wheel. Okay. Number 3 is the process of the electrical charge, that is the deviation of the cathode rays perpendicular to the direction of the magnetic field, and then confirmed using the electrical plates plus and minus. Cathode rays are attracted towards the positive plate, therefore it confirms the negative charge of the cathode ray particles. And finally, the cathode rays are originated perpendicular to the surface of the cathode by using a concave shaped cathode. The cathode rays are originated perpendicular, so that they are converged into the center of curvature. So, that is the everything about the properties of cathode ray particles. The 5 setups are there. So, it is very important for your MCQ paper. Okay. This is important for the MCQ paper. Okay, let us move on to the next part. Okay, after doing these 5 experiments, then Thomson did another experiment. So, this is not related, actually it is somewhat related to this experiment also, but he did a separate experiment and find a special property for cathode ray particles. Okay, write down the topic. Topic is charge to mass ratio. Charge to mass ratio of cathode ray particles. Charge to mass ratio of cathode ray particles. That means the charge divided by mass ratio. Charge to mass ratio of cathode ray particles. So, very important thing. So, Thomson did a separate experiment of his own, and he found a special property for cathode ray particles, that is the charge to mass ratio. Let us see what is this charge to mass ratio. Okay. So, here charge is denoted by the simple E divided by mass is denoted by simple M. They are the symbols. Okay, E over M ratio. You can call this as E over M ratio, charge to mass ratio. So, the Thomson find, okay, he experimentally determined the E over M ratio for cathode ray particles. Write down this one and you have to highlight it, because in MCQ paper you need to know who found the E over M ratio of cathode ray particles. So, that is the J.J. Thomson, same person who did the experiment to find out the properties of cathode ray particles. So, write down the note, you have to highlight this word, highlight the whole sentence. J.J. Thomson experimentally determined the E over M ratio, that is a charge to mass ratio, E over M ratio for cathode ray particles. E over M ratio for cathode ray particles. So, he found the experimental value for the cathode ray particles. The experimental value was 1.759 times 10 to the power 11. Charge is measured in the unit coulomb, capital C. Mass SI unit is kilogram. So, coulomb per kilogram. This was the experimental value for E over M ratio. Okay, write down. experimental value for E over M ratio, E divided by M ratio for cathode ray particle is, write down the value, 1.759 times 10 to the power 11 coulombs per kilogram. 1.759 times 10 to the power 11 coulombs per kilogram. Okay, this was the experimental value found by J.J. Thomson from his experiment. Okay, then next part is very interesting. So this was found by Thomson using his experiment, and then he thought to do a little bit some other experiments to find whether this ratio, this value changes with the residual gas inside the cathode ray tube. He wants to investigate whether this value will change by changing the residual gas, that means the gas inside the cathode ray tube. Then what he did was, he changed the gas inside the cathode ray tube. Type of gas. So let's see, for one experiment he used the oxygen gas. For example, he used the oxygen gas inside the cathode ray tube, then he evacuated the normal layer and filled the oxygen gas inside the cathode ray tube, and then he did his experiment and determined the E over M ratio when oxygen is inside the gas as the residual gas. So he get the answer as experimental answer as the 1.759 times 10 to the power 11. The same value was obtained. Then he changed the gas to nitrogen. He obtained the same value. Then he used argon as the gas, same value. He used carbon dioxide, same value. Okay, same value was obtained. He used another gas like let's see, helium, same value. So he obtained the same value for any gas he used inside the cathode ray tube. He used the same value for EOM ratio, that is 1.759 times 10 to the power 11 coulombs per kilogram. Then what he did was, he changed the metal of the cathode. As you know, the cathode and anodes they are plates, they are terminals, electrodes, they are made up of metals. Okay, so the metal of the cathode was changed. Okay, he can use, for one time he can use iron as the metal of the cathode, then he get the same answer. He used sodium as the metal of the cathode, metal that is made the cathode, then same answer. He used zinc as the metal of the cathode, same answer. Aluminium, same answer. Potassium, same. Magnesium, same. Whatever the metal that is made the cathode of the cathode ray tube, he obtained the same value, 1.759 times 10 to the power 11. This is amazing. Okay, so you can see for any type of matter, whether it is oxygen, nitrogen, argon, carbon dioxide, helium, or any type of matter including metals like this, he got the same answer for every case. In all the cases he got the same value. That's very important. Okay, write down. Then Thomson changed the gas inside the tube. Changed the gas inside the tube. And the metal of the cathode. can write it like that, EOM. No need to put a bracket, EOM. Ratios were measured. Ratios were measured. Ratios were measured. Thomson found that. Thomson found that. Thomson found that the E over M ratio is a constant, write down the value in brackets. Constant means this is the value 1.759 times 10 to the power 11 coulombs per kilogram, within bracket write the value within brackets, constant, this value, for all cases, for all cases, for all cases, for all cases. That means it is independent. It is independent. That means does not depend. It is independent of the residual gas. Independent of the residual gas. Residual කියන්නේ inside එක තියෙන අවශේෂ කියන සිංහල වචනේ. So that's the gas which is remaining inside the tube. That means that is the residual mean, remaining inside the tube. Residual gas inside the tube. Residual gas inside the tube. The metal of the cathode and the metal of the cathode. Metal of the cathode. Metal of the cathode. Metal of the cathode. Okay, so this is very important, because for any matter, whether it is oxygen, nitrogen, or any matter, for any matter, so when we used oxygen, nitrogen, whatever the matter, the cathode ray particles, they shows the same E over M ratio. So the what can we think, or what is the conclusion of this observation? So if whatever the matter we used inside the cathode ray tube, whether the gas or the metal, okay, as we obtain the same value for E over M, that means cathode ray particle is common for any matter. It's a common particle. Cathode ray particle is common. ඒ කියන්නේ හැම particle හැම matter එකකම ඒක තියෙනවා common. It's common for any matter, for any element or any matter. That's a common thing. As all the human beings contain 2 ears, so the ears are common for all the human beings. Whether he is Nimal, Kamal, Sunil, whatever the name, for any, even he is Sri Lankan, Australian, that is a common factor, common feature, that all human beings contain 2 ears, 2 eyes, they are common. Like that, cathode ray particle is common for any type of matter, any sort of element, okay. Therefore, it is very common, that's why you get the same answer, it's common, okay, common. So, for if we get how many ears are there for human, always 2, 2, 2, 2, 2, 2, 2, 2, 2. Whatever the man or woman is, 2, 2, 2, 2, 2. Like that, you get the same answer. Okay. So, that means this is common. Then Thomson thought, what is this? So, this should be a common particle. This particle is present in any matter. In any of the element in the world, it is common, it is also present. And he thought that negatively charged. So, negative charge means there is an electrical nature, negatively charged, charge is there. So, then he suddenly remember the word electron, because already the Stoney named the electron before this. Initially, Stoney named the electrical particle, or the electric particle inside the atom is as the electron. So, he just remember that the Stoney's word, and he named this cathode ray particles as electron. So, this is the discovery of electron. So, the scientist that who discovered the electron is J.J. Thomson, because he is the one who studied deeply about the cathode ray particles, their properties, and this experiment, EOM ratio, and finally concluded that the cathode ray particles should be electrons. Write down, it is very important, write down. Write down. Then he finally concluded that. Then he finally concluded that. Then he finally concluded that. Concluded that the cathode ray particles. Concluded that the cathode ray particles. Cathode ray particles are common. Cathode ray particles are common for all forms of matter. For all forms of matter. All forms of matter, and name these particles as. Name these particles as. Name these particles as electrons. Electrons. Highlight the word Thomson electron. So, electrons are discovered by J.J. Thomson. J.J. Thomson. J.J. Thomson. Electrons are discovered by J.J. Thomson. J.J. Thomson. He discovered electrons. Okay. He discovered the electrons. Clear? It's very clear. Okay. Okay, this is the story of the discovery, the found of the electron, discovery of electrons by J.J. Thomson. So, in MCQ's paper, we need to know who discovered the electron. So, it is the J.J. Thomson, the scientist who discovered the electron. Stoney was the scientist who named electron, who gave the name for the word electron, who gave the name as electron. But electron was discovered by several set of experiments as we discussed so on, okay, as we discussed up to now. So, due to this set of experiment, Thomson discovered the actually what is the electron in the atom. So, this electron was discovered by J.J. Thomson. Okay, this is very important. Now, the electron was found by J.J. Thomson. After this discovery, we have to talk about, there is a very important factor, that is about the charge of cathode ray particle, the charged. The charge or the value of E of cathode ray particle was found by a different scientist. His name was Robert Millikan. Robert Millikan. So, this was the scientist Robert Millikan. Okay, Millikan. He was a physicist, that means he was a physics scientist. He had his own experiment known as oil drop experiment. Oil drop experiment. There is no need to study about what is this experiment, you just need to remember the word, that is the oil drop. He did some sort of experiment using a oil drop. You know the oil drop, no? Some sort of oil drop. Okay, that is a physics experiment. Okay, using his oil drop experiments, he determined the value of the numerical value of capital E, charge, that is the charge of an electron. He found it as minus 1.602 times 10 to the power minus 19 coulomb. This was the numerical value of the charge of an electron, found by Robert Millikan by his experiment, oil drop experiment. Okay, write down. Okay. This is very important, you have to write in red pen. Put a star. So, no need to remember the name, okay. This was found in 1909, in year 1909, but do not remember the year, okay. In 1909, in red pen write this, Robert Millikan discovered a numerical value for charge of an electron, using his oil drop experiment, You have to highlight Robert Millikan, charge of an electron, oil drop experiment, those 3 words, very important. This is MCQ point, very important, you need to remember this. This is MCQ point. Okay. Right. Then, so in the next rule, right below, charge of an electron equals, that is the value of simple E, charge of an electron simple E equals minus 1.0602 times 10 to the power minus 19 coulomb, and highlight that. This is the charge of an electron, Okay. So, then let us see the next one. So, you have to know that Robert Millikan oil drop experiment determined the charge of an electron, that is minus 1.602 times 10 to the power minus 19. The numerical value is this 1.602 times 10 to the power minus 9. The minus value was put because the electron is this cathode ray particles electron is negatively charged, therefore that is why the negative mark is placed. Okay. If you see this without the negative mark, that is okay, that the value is the 1.602 times 10 to the power minus 19 coulomb. Okay. Then what did was, after this, now the E over M ratio is known, this is the ratio, E over M ratio is known, that is there. So, this is the E over M ratio for electron or the cathode ray particle, that is the electron, cathode ray particle is the electron. Okay. Then simple E value was found by Millikan, E over M, this ratio is this, E divided by M ratio is this. Value of E means the charge of an electron or cathode ray particle, that is known 1.602 times 10 to the power minus 19 coulomb, divided by simple M means the mass of an electron, mass of the cathode ray particle, no, mass of an electron. So, from these 2 experimental data, we can calculate by ourselves, we can calculate the value of simple M, that is the mass of an electron. So, you can put it here and you can put it there, you can change the 2 positions, then you get the value 1.602 times 10 to the power minus 19 coulomb divided by 1.759 times 10 to the power 11 coulombs per kilogram. By simplifying this one, you will get the value 9.108 times 10 to the power minus 31 kilograms. This is the value of a mass of an electron. Okay, write down. Using Thomson's E over M ratio, E divided by m ratio, E over m ratio, E over m ratio, and Millikan's value of simple E, Millikan's value of simple E, that is the charge of an electron, Millikan's value of simple E, we can calculate mass of an electron, as follows. Now just first write the E over m equals the E over m value, then substitute the value for the simple E, then subject the simple m and get the answer. Okay, calculate it.